Hi everybody. So what we're going to do now is draw resonance structures, and we've got a couple of examples here. And so we want to do a couple of things. A is we want to show how to push the electrons, right? So we're going to use curved arrows. And then once we have our resonance structures, we're going to rank them from most contributing to least. Alright, so on this first one, first thing we want to do is you tend to want to push electrons towards either a positive charge or something that's electron efficient. Alright, so this first red arrow is going to tell us that we're going to take these two electrons in the pi bond and push them onto the nitrogen. Alright, so let's draw what that gives us. So this arrow will indicate that we're going to go back and forth between the two structures. That arrow told us that we put a lone pair on the nitrogen. And then everything else we left alone. So we're just going to draw it the way it was. Right? Our oxygen had the two lone pairs, so it still has the two lone pairs, all the same bonds. Now, what you notice is we have a carbon and we took the two electrons away, right? We took the pi bond and put those electrons on the nitrogen, so that's where the lone pair came from. But now we stole the electron, so this gets a positive charge. Right? So now we have a carbocation on our carbon. One thing you'll notice about all these resonance structures is they always have the same overall charge. We may create more or less charges, but they're always going to have the same overall. So this was plus 1, it's plus 1 here. Alright, our next one, what we can do is take one of these lone pairs and push it down. Now if we draw this one, that gives us a double bond to the oxygen. We only have one lone pair now because we used one of them. And then the nitrogen stays exactly as it was because we didn't do anything to it, right? If we don't move any arrows, we don't push anything on it, it stays exactly the same. And now our oxygen gets a positive charge. And if you're ever not sure what the charge should be, we can work them out together. Let's do an example. Remember, oxygen has 6 valence electrons, and then we can do our valence electrons minus lines plus dots. Alright, so if we add that up, it's 6 minus, and then now if we look at the oxygen, we have 3 lines. So let's put 3 in here. Plus, we've got 2 dots, right? Our lone pairs, there's 2 dots. Equals plus 1. And so that's where the plus 1 charge comes from. Alright, so you can always use that to solve for the formal charge. Alright, now what we notice is we've got 3 resonance structures. We've got one on the left, middle, and right. And now what we want to do is rank them. And if you remember, the worst thing on a resonance structure is to violate the octet. And if you look at each of these, if we look at the oxygen, it's got its 2 electrons to this bond, 2 here, 2 here, 2 here. So the oxygen has this full octet. Carbon's bound to 4 bonds, so it's got its octet. And even the nitrogen with the plus charge has 4 bonds, so it obeys its octet. Same thing with the oxygen up here. It's got 2 electrons, 2, 2, 2, so that gives us 8 total electrons. So all of them have a full octet with the exception of this carbocation. Right? This carbocation only has 6 electrons, which means it violates the octet. So this is going to be our worst structure. And it's because it violates the octet. Alright, so that'll be the worst one. Now, the next thing to do is you want to match the charges. Meaning, if we're going to put something positively charged, we want it on the least electronegative. If we were going to put a negative charge, we'd want it on the most electronegative. And so if you remember, electronegativity goes towards fluorine on our periodic table. And so if we zoom in on this section here, it's carbon, nitrogen, oxygen, fluorine, meaning that oxygen is more electronegative. So if we want to put a positive charge, we want to put it on the least electronegative. So we're going to pick nitrogen. So this becomes the best structure and middle. Alright. Now, a couple things, if we look back at our structures, remember when you're drawing resonance structures, you never disconnect the molecule. And the way that this is going to happen is we're only going to move lone pairs and pi bonds. Alright, so that's the only thing we can move. And the charges will end up moving consequently, but we have to resolve for those structures. Alright, so we took this pi bond, pushed it onto the nitrogen. That's where the lone pair came from. If you remember, there's no hydrogen implied here because there's a methyl group out on the end. So that means there's this carbocation. It's only got 6 electrons, so it violates the octet. So that's why this was the worst structure. Right. And then this one has an oxygen with a positive charge. Oxygen is more electronegative than nitrogen, so it's worse to put a positive charge on oxygen than is a nitrogen. If it had been a negative charge, it's the opposite. Alright, let's try another one. Alright, so what we can do here is we can take this lone pair, push it into the carbon, and push those electrons up onto the oxygen. If we look at those two structures, what this lone pair is doing is it's actually moving in to make a third bond between the nitrogen and carbon. Right, so let's draw that. It started with 2 lone pairs, but since we used one of them to make the bond, we've only got one left. The carbon sits in the middle. And now what this second arrow tells us is that we're going to move those electrons up onto the oxygen. So now we're left with a single bond, but the oxygen has 3 lone pairs. And if you did the formal charge just like we did above with the lines minus dots, you'll see that that gives the oxygen a negative charge. Right. Same with the nitrogen, and we can solve for the nitrogen this time. Nitrogen starts with 5 valence electrons minus 3 lines and 2 dots, which gives us a 0. Oxygen, we can do the same. 6 valence electrons minus 1 line plus 6 dots equals a minus 1 charge. And so that's where the negative charge comes from. Now, one thing I want to point out is, do you notice on the top one we only move 1 arrow at a time? Sometimes we can do that, sometimes we have to move 2. And the reason you know on this one you have to move 2 is if we had just done this first arrow, what we would have done is put in 10 electrons to carbon, and carbon can't ever have more than 8 electrons. And let me show you what it would look like. Giving this carbon 10 electrons. And you can't ever have that. Alright, so it just doesn't have an orbital to put those electrons in. And so that's how we know that we had to do both these arrows together. Alright, so they had to go in a flow of electrons towards the oxygen. Alright, now, if we're comparing these two structures, we've got oxygen with a negative charge, we've got nitrogen with a negative charge. Both of these structures up here have a complete octet. So they're both equivalent in terms of octet. Now what we want to look at is which one of these matches the charge with the atom. And since it's a negative charge, we want it on the more electronegative atom. So that means this is the better or the more contributing structure. Alright. So they're both valid resonance structures, but if you had to rank them, putting the oxygen with the negative charge is better than putting nitrogen with the negative charge. And that's because the oxygen is more electronegative. Alright, let's try one more. Alright, sometimes we can do several resonance structures. So same as we've done before, let's take our negative charge and we're going to push it in here and then push our electrons up onto the oxygen. Alright, so if we draw this structure, we keep the carbon framework just the way it is. We didn't do anything to the portion on the left, so let's draw it exactly the way it is. And now what this arrow tells us is we're pushing these electrons in, and so we get a double bond here. And this arrow tells us we took the double bond and moved it up onto the oxygen. So we get a single bond, and then the oxygen gets an extra lone pair. Right. We didn't do anything to the right, so that stays just the way it is. And if we do our formal charge, you'll see that there's a negative charge on the oxygen, so it keeps our formal charges the same. Alright, if we wanted, we could put these arrows and push it back and up, and what that would do is get us back to our original structure. Alright, so we could do these 2 arrows to get back to our original structure. Alright, now the other thing we could do is take the negative charge and go to the left. So we'll hit here and push those electrons up. Right, so if we draw our carbon framework, this time the oxygen on the right stays the same with its 2 lone pairs. And now, since if we look at the blue arrow, we've pushed these electrons in here, so that gives us a double bond. And then this arrow shows us that we're pushing the electrons up onto the oxygen, and it gets an extra lone pair. So now instead of having 2 lone pairs, it has 3, and it gets a negative charge. Alright, so now we have a couple resonance structures. Alright, so we have the one on the right that had a negative charge on the oxygen. We have another one with a negative charge on the oxygen, and then with a carbon. So between them, these two are about equivalent. This one would be the worst, because it puts a negative charge on a carbon. Right? And we want to put the negative charge on the most electronegative atom. Alright, let's try one last one. So what we have here is a molecule that looks like phenol, but it's lost its proton. And so what we can do is push these electrons down. Same as we did before, if we don't do a second arrow, we're going to have too many bonds to this carbon here. So these two arrows have to go together. We're going to push these electrons down, and then we can push these up. So now if we redraw our structure, indicating what those arrows have shown us, we get a double bond to the oxygen. We lost 1 lone pair, so now there's only 2. We didn't do anything to these other 2 double bonds, so they stay exactly where they're at. But now we get a negative charge here. All right, and that negative charge actually symbolizes 2 lone pairs. Right? So we moved essentially this lone pair down to make this double bond, and then we took the 2 electrons from here and put them up onto that carbon. So there really is a lone pair sitting on that carbon. Now we can take those electrons and push them down and push this up. Now if we draw this structure, we still have the double bond on top to the oxygen with its 2 lone pairs. Now this arrow here tells us we're going to make a double bond between these 2 carbons. We keep the one on the far left, and now the lone pair goes on this bottom carbon, and it has a negative charge. Alright, we can keep going around the ring, push our electrons up, push the pi bond up onto that top left carbon. If we draw a ring, double bond to the oxygen, still there. Double bond on the right, we didn't do anything to. And now, this arrow tells us we're going to make the double bond here. So let's draw that. And we move the lone pair and the negative charge here. Right, and so now we've essentially moved the negative charge all the way around the ring, and we can get back to our final structure by pushing this in and back up. Right, and I'll draw this last structure. It gives us back our single bond, and it also puts the lone pair back on the oxygen, so now it gets back to our 3 lone pairs. And this arrow here tells us we're pushing in our double bond and the one on the outside. Alright, so what we've done is taken the lone pair, pushed it around the ring, spreading out the negative charge. And this resonance does a couple things. One is it explains why this oxygen is more acidic than normal alcohols, because the more places we can spread out the negative charge, the better. The other thing, and we'll see this later in the course, is that it'll show you how you can predict reactivity of a molecule, because everywhere you have a negative charge, it has some extra reactivity there. And you can use resonance to explain that reactivity. Alright, I hope this helps.